Okay, chemists, in this lesson, we're now finally going to look at how to interpret an NMR spectrum and combine it with a couple of other pieces of analytical information to elucidate the structure of a small molecule. No more matching up compounds, but just from scratch, can we figure out what the structure is given its spectral data and maybe some other pieces of information like its molecular formula? You could imagine getting that from some trial and error from a mass spec. So the first one very nicely gives us the molecular formula. It's only 3 carbons and 7 hydrogens, an oxygen and a bromine. The integration ratio is 2 to 2 to 3, and that adds up to 7. So these actually are how many hydrogens represented by each signal. There's only 3 types of hydrogens, 3 signals, and we see a couple of triplets and a singlet. For determining the structure, it's helpful, I think, to draw little fragments on top of the spectrum that would match up with what that signal looks like. So a 2 hydrogen signal all the way to the left, I'll just draw a carbon with 2 hydrogens on it attached to other stuff. I don't know what yet, but that's got to be a CH2 group right here. Now that's just the integration. That's the fact that it's 2. I can tell by looking at it that this is a very clean triplet, which means it has 2 neighbors. This is a triplet. So I'm thinking 2 neighbors. Remember, the n+1 rule tells me how many neighbors cause the splitting pattern. So I can actually modify my fragment guess and say, well, whatever the adjacent carbon is, it has 2 hydrogens on it and no more. Could be 1 on each 2 separate adjacent carbons, but it's a good guess to just put them on the same carbon. And once I look at this little piece, I realize, aha, I actually have 2 sets of a CH2 group. One of them could be one of the triplets, and the other could be the other. So a pair of triplets would indeed be caused by a CH2 directly attached to a CH2 group. Again, we don't know what else is attached to the molecule, but we'll figure that out as we keep going. Then I get to the 3 hydrogen signal. That must be a CH3 group. It's a methyl with no neighbors. And the fact that its location is in the 3s likely suggests that it's near a halogen or another electronegative element such as an oxygen. And we happen to have an oxygen in the formula. So I'm going to guess that this is actually an O CH3 attached to the rest of the molecule. So that explains that part of the compound where we have a CH3 group due to that group. And then just to complete the formula, go back and check. There's nothing else interesting in the IR, just sp3ch bonds, but I also have a bromine. And a bromine means I have a single terminal bromine. It'll only make one bond in its typical bonding. And those are the pieces of the puzzle, and there's only one way. Those 3 fragments can go together. I have 2 pieces that end up capping off the ends of this CH2-CH2 group. So if I draw it as a line structure, I'd have a bromine, CH2, CH2, and then an O-methyl. And then I can just confirm, do I have a 2 hydrogen triplet, another 2 hydrogen triplet, and a 3 hydrogen singlet? Yep, that's exactly what we have, and that is indeed the structure. So let's try another one, and then we'll let you try one. The one below it also gives us the molecular formula, 14 carbons and 14 hydrogens, much bigger molecule. And if I look at the integration ratio of the hydrogens, they have a 5 to 2 ratio. That adds up to only 7, but there are 14. So that must mean this 5 is actually indicative of 10 hydrogens, and these 2 are actually indicative of 4 hydrogens. This certainly looks like a singlet off to the right. This set of peaks down here, however, doesn't look like a singlet. This looks more like a multiplet. So it's likely this is a series of signals on top of each other, all in very similar chemical environments and splitting each other, but not in exactly the same position. The location alone is very informative. Up in the 7s, that's suggesting that I have a benzene ring, some type of aromatic hydrogen containing compound. It can't be just benzene. The molecule benzene with 6 hydrogens on it would be a single singlet and nothing else. But it could be a monosubstituted benzene, such as that. In other words, a phenyl group. And a phenyl happens to be 5 hydrogens. Well, if I have 2 of them, that would give me 10 hydrogens all in this range. That also takes care of quite a bit of the molecular formula. This is a big molar mass compared to the previous one, but it's such a simple spectrum, so there must be a lot of symmetry to it. And if I check some other things, well, this takes care of, if I have 2 of these, this takes care of 12 of my 14 carbons. So I only have 2 other carbons to account for, and they must have hydrogens on them that produce this signal up here worth 4. So between those 2 carbons, I have to have 4 hydrogens on them. They're only causing 1 signal, so there must be a lot of symmetry. And the only thing that would do that would be another back-to-back CH2 group. So just like up above, we have a pair of methylenes, a pair of CH2s right next to each other, but they're all identical hydrogens because they show up as one singlet, not splitting each other. So if I have one CH2 group and 2 phenols and you put them together, there's only one way to do it, and it gives us the correct structure. That would be a benzene, CH2, and another benzene attached. And remember, there's no splitting with the hydrogens in the middle because they are identical to their neighboring hydrogens, so they show up as a singlet in the spectrum. Okay, that's the first 2. Why don't you hit pause and see how much you can identify from the third one down at the bottom, given the molecular formula, and notice some interesting IR information as well, and then come back and check to see how you did. Okay, so looking at the molecular formula, we've got 10 hydrogens. Adding up our integration, 2 plus 2 plus 3 plus 3 adds up to 10, so these actually are how many hydrogens we have. They give us, for the first time, some interesting IR information. The 1700s, that's indicative of a carbonyl stretch, a CO double bond, either a ketone or an aldehyde or something like that. It's likely not an aldehyde, because an aldehyde would have a CH all the way up in around 10 or so, and I don't see that in this spectrum. I do see aromatic hydrogens. I see benzene hydrogens as a pair of doublets. I know that because of the location between 7 and 8, roughly. So we probably have a benzene ring once again. Our molecule is not big enough to suggest that there's 2 of them, but that takes care of 6, actually 7 of our 9 carbons in the molecular formula. And there's only 4 hydrogens on that benzene ring. And if you think about the different possibilities of how a benzene could be substituted to have 4 hydrogens on it and have 2 pairs of doublets, this would work if you had a di-substituted benzene where the hydrogens flanked 2 other groups that are attached on opposite sides of the ring, what's called a para-substituted benzene. We'll learn more about this nomenclature when we learn about aromatic reactions. But this would make sense if you think about those 2 hydrogens worth 2, because there's 2 in identical environments. Each has 1 neighbor, so each is a doublet, but they are the same doublets. I don't know which one's which, but one of them would be this doublet, and then there's another pair of hydrogens showing up as a separate doublet. You can imagine any other type of di-substituted benzene with 4 hydrogens on it, it wouldn't give this splitting pattern. So this pair of doublets is a red flag for a para-substituted benzene ring. So that's most of our molecular formula. We just have to make sense of the rest. There's 6 more hydrogens. They're each 3 hydrogen singlets, a little below 4 and even more below 4. So we have 2 CH3 groups. But the location of them close to 4 and the molecular formula with a whole lot of oxygens present suggests that they're not just CH3, they're probably O CH3 groups, and they're slightly different OCH3 groups. But one of them would explain one of the singlets, and the other one would explain the other. You know, one of them is one, and one of them is the other. So now I have my pieces of my puzzle. Per molecular formula, we've got 6 carbons, plus 1 more for the carbonyl, and 2 more for the methyls. That's exactly 9. We're good. We've even factored in all 3 of our oxygen atoms. We just have to put these together, and there's only one way that it can go together. If you have a benzene ring, it's para-substituted. One of the substitution is an O-methyl. The other one would be a ketone, or sorry, an ester in between the other O-methyl. And that is the structure that matches that spectrum. They also give us some other information like carbon-carbon double bond character and obviously CH character from the I. So those are just 3 practice problems to show you how we can interpret an NMR and turn it into the chemical structure of a small molecule.